Welcome in. In this video, we will very quickly recap what we know about fields. We'll overview the main points about fields and circuits, and then we will look at something new, power dissipated in a circuit. And we'll see one example. The first big idea that you need to know, electric fields exert forces on charges. Is that shown in the picture over here? Yes. You have a charge, positive Q. It's in a field, shown by green, and it feels a force. The force F is produced by the electric field. What's this equation? What's it have to do with the picture? When we look at the equation, we see it's talking about a force exerted on a charge. Well, wait a second. What exerts forces on charges? Electric fields. So what does E stand for? It's not energy. It stands for the electric field. Specifically, it represents how strong the field is. Some fields are really weak. They have a low E. Some are strong. Those strong fields have a high value of E. The next big concept has to do with work. An electric field does work on a charge as the charge moves through the field. Is that shown in this picture? Well, first let's look at what work is. Work is a force times a distance. Cosine of theta says to have work, you have to move in the direction of the force. You have to move in the direction of the force. So the force and the distance have to be at least partly along the same angle. Okay. What's this picture show? Does it show work being done? You have a charge feeling a force. And why does the charge feel a force? Because it's inside an electric field shown in green. So we have a force. Do we have a distance? Yes. The charge is moving a distance d. And is the distance in the same direction as the force? Yes. Theta is 0. The force is down, the distance is down, and the angle between down and down is 0 degrees. So yes, the motion, the distance, is in the direction of the force. Specifically, in this example, the force and the distance both have the downward direction. So they're in the same direction. There's a crucial concept, potential difference. Compare the equation for potential difference to the equation for electric field strength. The strength of the electric field is the force per unit charge per coulomb on a small positive test charge. As you take a small positive test charge and move it through a field, the potential difference is the work per coulomb that's done as the small positive test charge moves through the field. So it's this idea once more. So as the electric field does work on the charge, how does that affect the charge? What happens to the charge? As work is done on a charge, the charge's electric potential energy changes. If you hold a pen above the ground and drop it, as the pen falls down, it loses gravitational potential energy. The same thing is true of a charge. As the field pulls the charge down over some distance, the charge loses electric potential energy. This raises the question, what happens to the electric potential energy? Where does that energy go? It can't be created or destroyed. That brings us to the notion of a circuit. In a circuit, electric potential energy changes forms. So here's a circuit, but what is it showing? What's this up here? That's a battery. Why are there two ends? Because a battery has two terminals. And why are there these circles on the left side? Those represent charges. What's the battery doing with the charges? It's cramming them all onto one side. Now when you connect this, what's this line here? This line is a wire. When you connect the wire, think of it like this. The charges spill out from the terminal into the wire. Now, my proportions are all wrong. The wire is really tiny, and not many charges spill out. The battery is huge, and so it has tons and tons of charges. What's this down here? This is a resistor. And inside of the resistor, these charges are going to get repelled away from all the other charges over here. And if the charge is being repelled, that means there's an electric field in the resistor. Current I is the amount of charge flowing by a point per second. So if you imagine you're standing right here inside the resistor, you could stand and watch charges flow by, count up how many coulombs pass per second. That's the current. The final thing in our review is for you to consider, how do you know that potential difference is lost across this resistor? How do you know? Look at what's happening. There's a field in green, and there's a force in blue. As the resistor moves across the field, what happens? The electric field does work on the charge as the charge moves through the field. And when the work is done, the electric potential energy changes. So as this charge gets pulled along the field, it's getting farther away from its other buddies, and it's losing potential energy. The resistance of the device of the resistor is the potential difference across the resistor, or the potential difference lost from one end to the other, divided by the amount of current passing through the resistor. Here's the new part. Resistors consume electrical power, and the reason is because they use up the charge's electric potential energy. Electric potential energy is lost as charges go across the resistor. That's what we just saw. So the power is simply the rate at which this energy is consumed or lost. Here's the equation. The rate at which, delta T is in the denominator, that makes it a rate. The rate at which the electric potential energy changes. Having delta T in the denominator makes it a rate. For example, velocity is the rate at which, 1 over delta T, the rate at which position changes. And acceleration is also a rate. It is the rate, 1 over delta T, the rate at which velocity changes. So power then is just the rate, 1 over delta T, at which the potential energy changes. Now we know the equation for potential difference is the work per coulomb. But the work does something to the charge. What happens when the field does work? The potential energy changes. And in fact, delta EP, the change in potential energy, equals the work. So if we solve for delta EP, what do we get? What's delta EP equal when we isolate it? Q times V. If we replace delta EP with Q times V, what do we have? This. We could rewrite that as Q over delta T times the potential difference. So the power consumed by a resistor is equal to the current through the resistor times the potential difference across the resistor. We can write this equation a couple of different ways. In place of V, we could substitute in I times R. And when we do, we get P equals I squared times R. The other way we can write this is, instead of substituting in I times R for V, we could substitute in for I. I is equal to V over R. When we make that substitution, we see that the power is equal to V times V, V squared over R. And so these are the equations that let us calculate the power consumed by a resistor. Here's an example. We have a battery of EMF 48 volts. This is number H, part H from number 30 in your notes. The EMF is 48. Here's the long end represents the place, the big end represents the terminal where charges have big energy. So this is the positive terminal. The other terminal we call the negative terminal. Charge flows, positives flow out from the positive terminal. They all pass through the 6 ohm resistor. They continue on, and right here they split off into 2 branches. So these 2 branches are in parallel. The charge passes through the branches, and right here it all meets back up again. And it goes back through the battery. The battery pumps those charges, crams them all back together again, uses up chemical energy, and then the charges continue through the circuit. We're going to find the power dissipated by each of the 3 resistors. To do that, the first thing I'm going to find is the voltage, the potential difference dissipated by each resistor. Imagine for a second that you take a box and you put it on top of this parallel circuit. And you don't know what's inside the box. You cover it up, it's like a cardboard box or something, right? You look at the box and you say, this box is nothing more than a resistor. Now, inside the box, the resistance of the box comes from the parallel circuit. But you don't know about that. All you know is there's a single box, which you think of as one single resistor. And what's the total resistance of the box? You use the equation. 1 over R total is 1 over 12 ohms plus 1 over 12. And whenever the 2 branches have the same resistance, there's a trick. The total resistance is just half of either branch. So you look at the box and you say, this box has a resistance of 6 ohms. In fact, that 6 ohms comes from these 2 parallel branches. But you could just imagine it as a single resistor. Whenever you have the same resistance across 2 series resistors, they share the EMF equally. So this consumes half of the EMF. This consumes the other half of the EMF. And that means that when we look inside the box now, we open up the box, we see that in fact 24 volts is consumed across this parallel circuit, which means 24 is consumed by each. Each one consumes the full amount, 24 volts. And this agrees with what we know, which is that in parallel, the 2 resistors have the same potential difference. So now we find the power dissipated by each, or the power consumed by each resistor. For this resistor here, we can choose from the equations on the previous slide. I will use V squared over R. The potential difference across this resistor is 24 volts. We square that value. The resistance of the resistor is 6. And we calculate the answer. It comes to 96 watts. The watt is the unit of power. We look at these other 2 resistors and we realize, hey, they have the same resistance, the same potential difference, so each of these will have the exact same power that they consume, 96 watts. That's kind of handy. This problem turned out to be pretty easy. And if you want to know what's the total power dissipated in the entire circuit, the total power would just be the sum of the individual powers consumed by each resistor. You would add up the 96 watts 3 times to get a final answer of 288 watts. We weren't asked for that, but that's the power dissipated by the entire circuit.